Meglio. Um, I think last time we were at this point. This was the last slide. So we also introduced the default router, the meaning of the default router. That is corresponds to that's the spatial entry in the routing table with net mask with length equal to 0. And it's matching with any packet, but since it is the shortest possible matching entry, it will be selected only in case you don't have other matchings in the specific entries of the table. So this is why it's the default router, and the concept is that it's where a router hands over all the packets for which the destination is basically unknown. So this example shows the forwarding process in a router in details, and we are so talking about possible direct forwarding if the incoming packet in the destination address of the incoming packet is matching one of the interfaces. Otherwise, the forwarding will be indirect, and the router will have to perform a routing table lookup using the destination IP address as a key to look into the table. So the first step, in this case, the router has two interfaces. You can see here the configuration of the two interfaces. This is the IP address of each interface, is the first one, and the second is the net mask related to the network to which the interface is connected. So the first operation is to check the destination address against the interfaces. And as you know, there will be, in this case, maximum one match. So there is no ambiguity. You can have match with just one of the interfaces, or otherwise you don't have match with any. So in this case, we have this blue box that contains the destination IP address. We have to end it bit by bit with a net mask of a specific interface. Let's start with interface number 1. And then we have also to end the IP address of the interface with the same net mask. Notice that the net mask is always local, so it is configured in the interface. And then we have to see if the two results of these two operations are identical. So in this case, if you do the end with the first net interface, here you have you obtain on this side 131, 175, and 21.0. On the other side, you obtain 131, 175.21.0. So the two results are matching. Okay. So in this case, this packet will be forwarded by direct forwarding towards this interface. It means that the destination, the host which this IP address is directly connected to the network to which this interface is also directly connected. Okay. So the mechanism will be to deliver, as we have seen, to deliver the packet to the layer 2 implementation of this interface. Layer 2 implementation will look for the corresponding the MAC address which is corresponding to this host by looking inside the MAC table or R table of that specific interface. But the packet will be encapsulated in a layer 2 frame. Layer 2 frame will be sent to the destination. If you can see that you don't have a matching with the other interface, because in this case you will obtain 131.175.12, which is not matching with the .21. Okay. Next example, here we have a new destination address. This destination address is not matching with any of the interfaces, and the same will hold also for the next destination address we will see. So it means that this packet must be forwarded using indirect forwarding. So the router has to perform an IP address lookup inside the routing table, okay, using this address as the key. We start implementing the lookup in a very simple way. It's a manual lookup, but basically we will perform a linear search. It means that we start from the top entry in the routing table, and we go to the next entry, and then to the next, until we reach the bottom of the routing table. And I remind that when we are looking into the routing table, we will find multiple entries that are matching the destination IP address. In fact, here, if you start with the first, so it's not matching with the interfaces, we start with the first. Here we have the mechanism is always the same. You take the net mask, you make an end to a bit by bit with the destination IP address, and you take the same net mask, and again you make a bitwise end with the network prefix. Actually, this second operation is not needed, because here you have already the network prefix directly, so you don't need to make an end, bitwise end. Here you have already the result here, so we just make the bitwise end with the destination address, and you can see that in this case we don't have matching. Then with the second entry we have matching. We do have matching because it's 31.175.16, the same as the result here. Then we don't have matching with the third, we don't have matching with the fourth, with this. The final one is always matching with any incoming packet, so we have matching also here, okay? However, we have to apply the longest prefix matching rule, so we must select the entry which is matching with the incoming packet, the destination address, for the highest number of bits. That is also the longest prefix. So the result will be this one, okay? This packet will be sent where? It will be sent to the information, the IP address which is written here. It's an IP address of the next hop router, or actually better, the interface of the next hop router, which is connected directly to this router here. So then we have to make an indirect forwarding, you exploiting the interface of this router, which is connected to this next hop router. Here is first hop, is sometimes you can call it first hop or next hop, is the same. In this case, this next hop router has an address which is 131.175.21.2, which is matching with the first interface. Okay, so it means that this destination, this next hop router is connected to the same network as this interface. So this router here, which owns the routing table, will have to take the packet, create a framework, layer 2 framework, in order to transfer the packet to the next hop router using the MAC address, which is corresponding to this IP address found in the MAC table or ARC table related to this interface number 1. Okay, is it clear so far? Next example. Okay, I go a little bit faster. This is not matching with any of the interfaces, so we have to make IP address lookup on the routing table. This is not matching with all these entries. it is matching with this entry here. It is also matching with the next entry, and it is matching with the default router, of course. Notice that this prefix here is contains or corresponds to a block which is a sub block of the next prefix, this one. Okay. However, since we always apply the longest prefix matching rule, we will have to route the packet towards this next top router, okay, because this is the more detailed information, routing information corresponding to the smallest to the smaller network. Another example, this is not matching with anything except the default router, so it will be handed over to the default router. Okay, it means that this router has no knowledge, specific knowledge of the destination of this destination IP address, or the better of the network which contains that IP address. Notice that most of the routers have this entry, that is the default router, but not all the routers have default routers, and in particular routers that are at the core of internet, so that belongs to tier 1 large service providers. They don't have default routers, because otherwise you would have an infinite circulation of packets that are bounded to the destinations that are unknown. There are some IP addresses which are in principle valid in terms because they can be assigned to host, but however they don't correspond to anything, because, for example, that specific host is not active, or that specific network that contains the host has not been assigned, or is not active, or other reasons, so in that case there must be somewhere a router that discards that packet. Okay? If all the routers have default routers, that packet will circulate indefinitely. Last information about addressing is address aggregation, which is basically the opposite of subnetting. In fact, it's also called supernetting. Address aggregation is the extension of the concept that we have already seen, but that packets are routed according to not the destination IP address, but the destination network. This is the first level of aggregation. But we can do something more, and this is to reduce the size of the routing tables in routers in internet. Let's consider this example here. We have these 4 networks, which are different networks that corresponds to the different blocks, and they are all connected to this router here. And so in order to send the packet to any of these networks, we always have to go to this router. This router is the next stop router for all the destinations that are contained in these 4 networks. So in the routing table of router 2, in principle, we should have one entry for each of these networks. So this is an example of a possible routing table in router 2. But you can notice that all these entries all have the same next stop, okay? Same next stop information. And also we can notice that all these entries corresponds to blocks, to address blocks, which are contiguous. Okay, this is the first address block. Then we have immediately the second one. So the top boundary of this address block is next to the bottom boundary of the next, and so on and so forth. Okay, so we can do something in order to reduce this information which is redundant. and this is in favor of reducing the size of the routing tables, because of course the larger the routing tables, the more expensive is software and hardware that routers must be implemented. But also when we have large routing tables, we have also the updates. That means exchange of information between routers. As we will see, they require routing protocol messages, and if you have many entries, you have to do many updates, so a lot of exchange or chatting between routers for the routing protocols. So we can reduce the size. One solution could be to make this R3 the default router of R2. In this case, you can eliminate all these entries. But this is a little bit not flexible, because, for example, R2 may have various routers in the same situation of R3 that are connected. So you cannot solve this with simply specifying the default router. So the best is route aggregation, which is possible whenever you have entries that are contiguous and also with the same information about next hop. Okay. How can we do it? It's very simple. When we wanted to subnet a specific range of addresses, we extended the net mask. In this case, we want to aggregate, so we shorten the net mask. And for instance, in this case, this is the binary representation of the addresses. So you can see that they are the same, they have in common the first 2 bytes and up to the 6th bit of the 3rd byte. The last 2 bits of the 3rd byte are different, so we can aggregate them by shortening the net mask by 2 bits. Okay, so this was the original net mask with 4 bytes of network prefix and last of host ID. So we can now use the net mask, which is 255, 255, 252. Okay, we have shortened it by 2 bits. And this means that we will be able to represent all the 4 networks with a single network prefix, which is this one, which in decimal notation would be 213.2.96.0/22. Okay, before we had /24. So when you are doing this supernetting operation, this is the resulting routing table of router 2. As you can see, the 4 separated entries are now replaced by a single entry. And in terms of routing, the result is perfectly equivalent. It's exactly the same as before. So the condition is that address blocks should be adjacent, and in order to favor these, of course, the policy of allocation or distribution of address blocks should be say, matching this rule. And in fact, today address blocks are usually assigned on a geographical base, so it's easier to have these aggregations of adjacent blocks that can be used in order to simplify the net mask. This is another example of supernetting. Here we are decreasing the net mask by 3 bits, and you can see also the reverse or opposite operation, which is subnetting, increasing the net mask by 3 bits. So when you are decreasing the net mask by 3 bits, it means that you can aggregate 8 consecutive contiguous blocks. This is an example that puts together subnetting and supernetting. So here you have a network here, which is locally divided, so subnetted by different subnets, and there are routers A, C, B, and E, which are external. And so in these routers, the whole network, which is 162.12.0.0, can be seen by a single entry. While when you are inside the network, you have different entries. So the subnetting is simply implemented by providing different entries into the routing table of router D. Okay. So let's take two packets. This is one packet with destination address 162.12.34.75. This is another packet. Both the destinations are inside this big network, but they are on different subnets. So while the packets are traveling outside the network, it's also class B networks, where the packets are traveling outside the network, they can be routed according to the external, so this single prefix. The prefix corresponds to the network 162.12.0.0 with a net mask which is 255.255.0.0, and the subnet mask instead inside, which is defined in the subnets, is /27, okay, because here you have 255.224. 224 means 111, and then the rest is 0, so it means that subnetting is done by extending the network, the original net mask by 3 bits. So routing outside is only based on the general entry. So both these two packets have a destination address which is matching with the entry 162.12.0.0 in the routing tables. So both router E and also router A and B will send, and also C will send the packets towards router D. Okay. Once the packets arrive in the router router D, sorry, they will be routed according to the subnet, because in router D you can see that the routing table is more specific and it has subnetting configured. So one of the packets is matching with the first entry, the other one is matching with the second entry. Okay. The first entry is .64 in the last byte, which means 010. The other one is .32, which means 001. Okay, so this is a subnet number 4. This is subnet number 1. And you can see that the next hop information is different for the two subnets. The first one will be forwarded towards this router here. The second one will be forwarded towards this other router here. Okay. And here you can also see the two destinations. One is in subnet, the first subnet, the second one is in the second subnet. So this is the routing of the first packet. As you can see, the destination .75 means that you have in the last byte 010 and then the host ID. 010 is matching with .64, okay, subnet that is .64. On the other case, you have 001, which is matching with subnet .32, and so the other packet will be sent there. Okay. So route aggregation is efficient. However, in some cases, it is necessary to propagate the aggregated set of routes, but also specific routes. Okay, so more specific routes. So this is an example of a route aggregation that is carried out on these blocks. So another example of route aggregations. Here we have /23, and the comprehensive block is /20. Okay, this is to aggregate all these networks, and this is another network. So what I was referring to before is the exception routing. So in this case, you can see that we have this block, which is the same as in the previous slide, but then we have this block which is separated, and you can see that in this case we are adding to the routing tables of routers that are here these are the entry, which is the same as in the previous slide. So all the packets that matches with this entry will be sent to in this area, in this network. But also we are adding another entry, which is a new network sharing the same path with the previous one. But you can notice that this new entry is a subset of the block 200.23.16.0/20. In fact, here you have 200.23.18.0/23. Okay. This is called exception routing because it means that you have to send all the packets that are matching with this entry here, and this entry is the aggregation of this network, except, this is why exception, for packets that are also matching with this more specific block. Okay, and this more specific block is located in an area in another place. So the packets that are matching with this specific block have to follow another path. Why we need exception routes? Obviously, this is against the reduction of routing entries we have talked about before. Okay? But in some cases, it's necessary. This is a geographical example. As we said, in order to favor aggregation, today the network addresses are assigned on a geographical base. So imagine that you have a company that is located in Europe, for example in Paris. The company will ask for a set of addresses. Let's say, for example, it will ask for 194.0.0.0/7. Sorry, it will ask for a set of addresses that is within this block. Since the headquarters is in Europe, it will be given a subset of this block. Okay. The block 194.0.0.0/7 is a very large block, which is usually assigned to the local authorities in Europe, which are then distributing this block to the companies, the European companies. Imagine now that this company decides to open another site in a different place, for example in South America. So in principle, the company should ask for a new block of addresses for the site in South America, and it will be given a block that is belonging to the block that is usually used for South America. However, it means that the company has to reconfigure all the machines that are being shipped to South America for the new site. Okay, and this is usually not very convenient. So it is preferable that all the machines of that company will keep the original IP addresses, and therefore there will be part of the IP addresses that are assigned to the company which will be located in another place. So in this case, this is the block that goes from 195.0.16.0 to 195.0.23.0. Okay. So it corresponds to the network. Corresponds to the network 195.0.16.0/21. Okay. This is a subblock of the more general European block, but is located in another place. So when we have a router outside, for example, in New York, so it's in another region, how can we configure the router? If we only use address aggregation, this router will have a single entry which corresponds to the European block, for example. And in this case, assume that the router receives a packet that is as a destination a host belonging to that company, and by chance the host is located in Mexico. Okay. So if this router has a single entry, which is the large entry of the European networks, this packet will be sent to Europe. Okay, and then probably in Europe there will be a way to find the route to the destination, but it means that the packet will be sent again to New York, let's say, and then or to another router, and then to Mexico, or there will be another way to go to Mexico. But in any case, the packet was transferred to Europe, so at least twice, it crossed at the Atlantic Ocean in an unnecessary way. Okay. So it's much better to configure the routing table of a router that is in New York using exception routing. So configuring not only this general entry for Europe, but another entry with this network, which is 195.0.16.0/21, having the router in Mexico City as next hop. Okay. So the meaning is when you receive a packet that is going to this macro block, route it to Europe, except if the packet falls into this smaller block. In that case, route it directly to Mexico City. This is much more efficient in terms of routing. Obviously, you have to create two entries instead of one, so it's worse for the size of this routing table, but it's something that is done quite frequently. Okay. Another example is when a company is a customer of a specific service provider, and then the company decides to change the service provider. Okay. So in principle, the company should take the new block of addresses from the new service provider, but this means that it has to reconfigure all the machines. So in some cases, the company will keep the IP addresses of the old service provider, but it will be reachable from the new service provider. So you will have to create exceptions inside the routing tables of the external routers. Today, this exception routing is a problem because exceptions are many, so routing tables are inflated by this technique, but it's something that is not very easily avoidable. Okay, this is the end of this. Here you have a routing table that you can find in Linux systems. Also, the hosts have routing tables. Okay, so if you have a PC, you can look into the routing table of the PC. that is, all similar to the routing table that you may find in the router. And in Linux system, this is the format. So you can see that you have the main columns, which are net mask, destination, next hop, interface, which immediately tells what is the way to send the packet when you have next hop. So you don't have to find the network, the interface where to send the packet. And then you have these extra columns. One is for flags. Here you can see the meaning of these flags. Metric, and the use, how many packets matched that specific entry so far, and so on. If you want to have the Windows version, you can go to the command window of your PC and use the command root print. Root print will display a similar table as this. Okay. Okay, that's all for this week. So next week we will go on with the layer 3, trying to finish the other things that are left, and then entering the routing chapter. We will discuss some routing algorithm. Okay, thanks.